Thank you for the introduction. So as Xavier just said, I will introduce you the abstract interpretation, which is a static analysis tool. So let's go. So let me start with a simple question. Here is a small program. It asks for some value of n, squares it, adds 4, and runs a loop. And at the end, divides 10 by n. And the question is, can n ever be 0 when we reach the division? So it seems obvious that it cannot. After all, n is n squared plus 4, which is always at least 4. But can we be certain? And more importantly, can a machine be certain for any possible value of n? So the natural answer is let's taste this. So here I put a few values of n. For example, with 4, the final n will be 34, and so it's safe for the division. If n starts at -2, at the end it will be 22, so it's one more time okay. For example, if n is equal to 0 at the beginning, it will end the program with 18. So one more time, it's safe for the division. But testing is finite. The set of execution is infinite. No matter how many tests we run, there is always an input that we haven't treated. And this is the property that Rice proved in 1953, that any non-trivial semantic property of programs is undecidable. That means no algorithm can answer this question correctly for all possible programs and with all impossible inputs. So this is here. What can we do? We want a tool that is able to reason about all the possible executions at once, which is automatic and gives a formal guarantee about the property we want, and which always terminates because it's unuseful if it's never terminates. So this is exactly what abstract interpretation provides. It was introduced by Patrick and Radia Kuzo in 1977, and it is a mathematical theory for computing sound over approximations of program behavior. And this theory is automatic. And we will see what this means precisely in a moment. So in this talk, we are going to ensure that the introduction program never performs a division by 0 using abstract interpretation. First, we are going to, I'm going to introduce what abstract interpretation is. After, I will show you a case study, ASCPP, which is a tool that I made in C++, which is a toy tool doing abstract interpretation for a language, for the while language. And after, we are going to explain the limits of the tool. Through this talk, I will use the minimal imperative language called while, which is inspired by the while language from Bernard Gros. So I have three statements in the AST: arithmetic expressions, Boolean expressions, and statements that includes sequencing, assignment, if statement, and while loops. So this little language is Turing complete, so it's expressive enough to be interesting, but simple enough to analyze it formally. So let's go on our first section about what abstract interpretation is. So before we can analyze a program, we need to choose what we want to reason about. In our example, we want to ensure that at the end of the loop, the while loop, n could never be 0. So the choice is called the abstract domain. We need to choose a domain to let us prove different properties. For example, the sign domain tell us whether a variable is positive, negative, or 0. The intervals domain tell us the range of value, the range of the range of a value can have. The congruences can reason about the positivity or negativity of a variable, if it's always even or odd. Sorry. And after we have very complicated domains like octagons and polyhedra, which let us to reason about relations between variables. So in this list, there is a little hierarchy, and the last one of much more complicated than the first ones. And in this talk, I will use the interval domain either to show you what is abstract interpretation, and for my little tool, I use also the interval domain. Okay. So now that we know the domain, we can see that like in this example, we have two words: the concrete domain and the abstract domain, and we have two functions, alpha and gamma. So the alpha is the abstraction function, which takes a set of integers and returns the smallest interval containing it. So for the example, if in the concrete domain we have 1, 2, 3, and 6, it will abstract it to 1, 2, 6 interval. And we have the gamma function, which is the concretization function, which takes an interval and returns all the integers it contains. So if we are going back in the other direction, it will contain 1, 2, 3, 4, 5, and 6. And then we have two properties. The first property says that concrete values are always included in the concretization of the abstraction. For example, in the set 1, 2, 3, 6, it is included in 1, 2, 3, 4, 5, 6. And the gamma, yes, and this is this operation. We may always add elements, but we never lose elements. And the second property says that re-abstracting a value cannot give us something more precise than the original, because as we said previously, if you go back from the interval 1 to 6, it will give 1, 2, 3, 4, 5, 6. Okay. So let's talk about the interval domain that I used. An abstract value is an interval over the integers, and I have two special cases: top, which represent complete ignorance, we know nothing about this variable, and bot, which represent an unreachable state. I also have the arithmetic operations that are lifted from integers to intervals. The addition is very simple. The minimum possible sum is A plus C, and the maximum is B plus D. The negation swaps and negates the bound. Multiplication takes all the four corner product and takes the mean, the minimum of AC of the products AC, AD, BC, and BD, and the maximum for the higher bound AC between all these four corners. So let's see the example. So for the intervals 1, 2, 3 plus -2 to 5, it gives with the addition -1 to 8. And the two last example are for the multiplication. So the first one is only positive. So we have 2 to 3 times 5 to 7, which gives 10 to 21. And the third example is -3 to 2 times -3 to 2, which gives -6 to 9, because we take the minimum for the lower bound, we take the minimum product. So it's -3 multiplied by 2. And for the higher bound, it's -3 times -3, which gives 9. Okay. So it's cool to have operation like multiplication, addition, and negation. But what if we have an if statement, a statement that branches the program? So when a program branches, both paths are possible, and we must account for both. We use the join operation, which gives the smallest interval containing both results, as you can see in this definition. So let's consider this program where x becomes x plus 100 if x is superior than is larger than 5, and in the else case we are doing x minus 1. So at the initial state, the store of x is 0 to 10, because we consider this program starting with this store. For the then branch, we have this addition. So we are going to make the classical addition on the two intervals. So it gives at the end the x is between 100 and 110. On the else branch, we start back from the original store, and we are doing the addition between 0 to 10 plus -1 to -1, and this is giving a -1 to 9. And at the end, we join the two results of each branch, which gives -1 to 110. Okay, so it's kind of easy. And now let's talk about the while loops, because this is an interesting case. So let's consider this simple program. I starts at 0 and increments forever. Okay, so the initial store is 0, 0. After the first iteration, I is 1. So we join with the initial store and we get 0 to 1. After the second iteration, I is 2. We join and get 0 to 2. And after n iteration, I is between 0 and n. And this is a problem because it never stabilizes, so it loops infinitely. Because the interval is keeps growing. So we are searching a store big X, such as f of big X is equal to X, where f is the loop body. And this This thing is called a fixed point, and it has been concepted by Tarski in 1955. Yes. So, however, in our program here, it's not enough because the interval lattice, the chain is infinite. So our naive iteration may never reach the fixed point. The solution is widening, which has been introduced by the Kozo couple in 1977. And the idea is simple. If a bond keeps growing across iteration, we can jump to infinity immediately, as you can see here. So if the lower bound decrease, we send it to minus infinity here. If C is lesser than A, and we keep A otherwise. And for the higher bound, we jump to plus infinity if D is greater than B, and we keep B otherwise. So on the previous program, after using widening, we have I still start to 0 to 0. After one iteration, it is 1 to 1. The upper bound grew because it was from 0 to 1. So the widen operator calculate the wide interval to 0 to plus infinity. And if we do one more iteration, it gives 1 to plus infinity. And as 0 to plus infinity is included in, yes, 1 to plus infinity is included in 0 to plus infinity. We have reached the fixed point because it satisfies the fixed point thing, calculus. So we can use the widen interval at the end of the while loop. Okay. So widening guarantees the termination at the cost of some precision, but we will talk about this at the end. Yeah. So now we have a better idea of what abstract interpretation is. We are going to jump to the case study, which is my tool ISCPP, which is a toy static analyzer in C++ for the while language. So the pipeline is very simple. It takes the while program in parameter. It lets it into a list of tokens. After it passes it into an IST, and it runs the abstract interpreter and output the abstract store, which contains the interval of each variables at the program exit. Okay. So I want to tell you first, how do we represent intervals and stores? So the store maps the name of the variable to its interval here. An interval is represented by its two bounds, the lower bound and the higher bound. The isBot is just a boolean that says that it is bot, so the unreachable state. And each bound is either negative infinity, a finite value, where the value is stored in this variable, or the positive infinity. So I wanted just to add something. that having the sign of the infinities is important only for the multiplication, because when multiplying two infinite bounds, you need to know their sign to determine the sign of the product. So when I added the multiplication, I needed to change the representation of my intervals, because before I just had an optional integer, which is if it's infinite, it was known, and if it's finite, it stored just the value of the bound. Okay. Talking about the AST, which mirrors the grammar of the while language that we saw previously, and the abstract interpreter propagates a store through arithmetic and statement nodes, not through the Boolean expression, because the Boolean expression determined the control flow. Sorry. Yes, the Boolean expressions determine the control flow, but in my tool they are not used to refine the store. For example, when we enter in a while loop, and the condition, for example, is I less than 10, we do not use that condition to narrow the interval of I inside the body, because we can imagine that at the end of in the body, it I will be I 0 to 10, and not and my tool at this state will tell 0 to plus infinity. And this thing is called guard refinement, but it is a future work for my tool. Okay, so let's go to the propagation through expression of the store. So it's very straightforward, because a constant n gives the singleton interval n to n. A variable lookup returns the interval from the store, or both if it has not been assigned yet. The addition and negation apply the interval operation we saw earlier. And for the multiplication, I have two cases. Here is the classical multiplication at the end. And here I have the square operation, which has some helps to help my tool to automatically say return 0 to plus infinity if the bound were to infinity. But in the classical multiplication, my tool over approximates, so we lose a lot of information, and it always say top, so minus infinity to plus infinity. Okay, so this is a little hack, but it's also a hack that appears in real tools, so why not? Okay. And now about the propagation through statements. So the skip returns the store unchanged. The assignment updates the store with the evaluated interval. Sequencing chains to evaluation and update the store at each time. And after we have the if then else that use the join of the store after the two evaluation of the branches. Okay, and if we have only if then, the S2 will be skipped. This is implemented in the when the AST is constructed. Okay. And here I put again the example that we saw earlier on the join. Okay. So how do I handle the fixed point iteration? So we compute one iteration to get S1. We use the wide operator through 0 with through S1. And after we loop with S next, which is the second iteration on the body from the using the store S wide. And if S next is included in S wide, I return S wide. And here is an example. So n starts at 4 to plus infinity after the squaring in our algorithm. Yeah. One iteration gives 5 to plus infinity. The widening gives 4 to plus infinity here. And here is the next iteration, 5 to plus infinity. And we know that we reach the fixed point because 5 to plus infinity, the S next, is included in 4 to plus infinity, the S wide. So we return the S wide. Okay, and here I put the actual run of our program that we want to check. And here is the output of ASCPP. So we are considering the store at the start and is stop. So it's minus infinity to plus infinity. We have this program except the last line because we want to know the store before the division. And in the output, the tool actually said that n is always between 4 and plus infinity. So the conclusion, since 4 is greater than 0, the denominator is always never 0, and the division of this program is always safe for all value of n. Okay, so now let's talk about some limitations of my tool. So first, as we previously talked about, I don't handle the quad refinement. So the loop conditions do not refine the store. So I should I want to add it because it can make my tool very much precise. There is also no relational reasoning between the variables, and this is to fix this. We can handle other domains like octagons and polyhedra. The third point is a little close to the first one because my widening algorithm lose a lot of precision because if in the while loop I is going from 1 to 10, for example, it is approximated to 1 to plus infinity and not 1 to 10. And this can be handled to one more time gain in precise size. Yeah. And yes, I use the while language, which is limited. So I didn't implemented the division or the modulo. So I can add first these two operations and maybe in the future add a richer language to handle more structure. And to finish with, I wanted to talk about the real tools that use the abstract interpretation in the industry. So, for example, we have Astray, which use the domains of intervals and octagons, and uh, they could they have proved the flight control software of the Airbus A3080. There is also Freemacy that use a kind of abstract interpretation and infer that is developed at Meta. Okay, so let's summarize and conclude this tech talk. The abstract interpretation is a mathematical theory for computing sound over approximation of program behavior and automatically with formal guarantees. I made the ASCPP toy tool in C++, which use the abstract interpretation on the domain on the interval domain, and I implemented fixed point, the fixed point iteration, the widen operator, and I proved with this tool that the program we saw at the beginning starting from a completely unknown n, proves that n is always at least 4 at the division point. And I can naturally add some extensions to my tool to gain in precision. For example, I can add the guard refinement, the relational domains, and after a richer language. Here are the references, and thank you for listening me, and I'll be happy to have some questions.
Thanks a lot, Charlene. It was very interesting and very well prepared. I have some small question, and so I will ask the full question. So the first one, in which context did you start this project? The second one is, will you continue the maintenance of the project? And the third one is, why C++?
So the first one was why starting this project. So the abstract interpretation and static analysis was in my big list of interesting domains that I want to explore from a very long time. So I took the last hacking days to do that. Why C++? I was interested in some potential jobs in C++, and I also wanted to. So I thought about what was the first programming language that I learned, and it was C++. And I didn't do C++ from a while, and I wanted to practice again. So this was a lot of um, thing that made me making this project. And I forgot your
Uh,
second question.
yeah, the second one was, will you continue the project
Yes,
or?
yes. When I will have time, but yes, of course. Because I think I used only the basic of abstract interpretation, and I want to know even more how can we uh, have a precise thing. And I saw that when you change domains, you can have a very cool graphics or thing that draw the intervals and for the polyhedras and the octagons, you can draw something, and maybe there is something to do to mix drawing and mathematic things.
Thanks a lot. I think that Ali has a question.
Yeah.
Thank you very much. It was a very interesting talk. I had a question about, have you considered maybe trying some other data types from integers? So that could be a lot of things. Like it could be floats or variants or records or something. And how does that translate?
Your question is, how do my tool translate to intervals? If I
No, I
change
mean, have you considered adding that? I mean, obviously in the wild language you don't have that, but that's
yes.
maybe an interesting avenue to explore.
Yes, that's true. And there is a lot of thing to do with float. A lot of issues in programming. Yes, and I think it is not very difficult. I think to move with intervals, to move from integers to float. Yes.
Yes,
Thank
Sean.
you.
Yeah, thanks indeed for the very nice presentation. I understand the topic a little bit now, and I think I didn't really before at all. This is actually just a follow-up to Ali's question, I think. In the example you were giving, my first thought was like, oh, of course, because you could hit the max int and then you'll wrap around. But you're obviously dealing with like real integers or like, I don't know, like unbound integers, not machine integers. So do you know if it adds a lot of complication to the abstract domains if you need to deal with this kind of wrapping behavior, or is that like fairly, you said like floats are fairly easy. I guess those usually wrap around too. Does like widening work the same way, or does it just wrap around? I don't know if that's a well-formed question.
I think I understand. Maybe at some points it can be more difficult, but in my opinion, the big difficulty is to have a more precise interval at the end of widening or join or other thing, instead of changing the values. But I might be wrong. I don't know.
Thanks.
I don't know if it answers.
I'm not sure either, but I'll think about it. I don't know enough about the domain to know if that answers, but thanks.
Maybe if nobody has any question, I can ask a last question. What is your global feeling about C++ versus OCaml?
So I built an entire IST in C++. It was way more difficult than in OCaml, and it's funny because I'm thinking in OCaml. So I wrote something close to OCaml. If I can show you, do you still see my?
Yes,
Yes. Is it big enough?
perfect.
Okay. So, for example, I used a variant which is close to something, and this it it is not probably it's probably not the more efficient way, but in my head it was like this in OCaml, so I mirror it in C++. So I'm sure that it will be way more easier in Okabo.
Haha, Camel's victory.
Yes.
Thanks a lot, Charlene. If nobody else has any question, I see that you still have your hand raised, Ali. Maybe you have another question?
I re-raised it. Yes, I have one more
Okay.
question.
Let's go.
I think in compiler optimization, they've done a lot of kind of work in like theory about how to kind of combine for loops and transform them into kind of similar for loops so that they can be optimized better. I wonder if you've kind of considered some of that work that might help with analyzing the loops that you have in more like finer detail.
So I want in the future work to handle the BX, the Boolean expression, to add refinement. So it will analyze more my the actual structure of the program. Is what is it
Yes,
your question?
I mean it's kind of a question and a suggestion fused together. But if you like, I can message you some further reading on that if you want.
Yes. Please do.
Can we stop the recording?
Yes. I don't know if I still share my screen.
No.
No. Okay.
Perfect.